I'm Tatiana Perrotin, and I'm going to talk about my work on the design, simulation, and testing of low-power cylindrical Hall thrusters in the plasma propulsion group. For those who don't know, annular Hall thrusters are the traditional type of Hall thrusters, and they are one of the most mature and common in space electropropulsion technologies. They are pretty popular for their high performance, specifically their high thrust. But most of them, the existing ones, are high power or medium power ones. And now with small satellites being more and more used, we need to develop low power propulsion solutions. And this is challenging because we don't know scaling laws, and efficiencies drop as we decrease the size and the power of the thruster, almost with other engineering problems that arise. And the cylindrical Hall thruster is a rather good candidate for low power because we remove the internal pole, so we remove opportunities for wall losses. Or some other aspects are also a bit easier. It's not conventional, and there are a few prototypes that exist. So there is room for research on those kind of thrusters, and we need experimental data to improve our capability to model those thrusters and to optimize them and better understand the physics, of course. So the main objectives of my thesis are centered around optimizing the performance of the cylindrical Hall thruster at low power. For this, I designed two prototypes and made them sort of modular to be able to test different magnetic fields or injectors, these kind of things. And I characterized their performance and their plasma properties. Some work also focused on the neutralizer, the election source that goes with the thruster, and about coupling numerical work, specifically providing experimental inputs for simulations. At the beginning of my PhD, I did some simulations with the hybrid code of the group, hyphen. And more recently, I've provided a set of experimental data for Iñaki that presented yesterday, his teaser, to run new experimentally informed simulations with this code. I also, along my PhD, developed some diagnostics for plasma thrusters, and in particular, here you can see emissive probes. And then coming to the testing of the thrusters themselves, as I said, I designed and built two prototypes. And in the first campaign, I used various types of probes to measure the plasma properties in the fire plume of this thruster. You can see here some results of that campaign. In the second campaign, I looked instead inside of the discharge channel with laser-induced fluorescence spectroscopy to measure the ion and atom velocity distribution in the channel, which is something very useful both for and to understand the geometry of the plasma inside of the thruster and to inform models. And the latest test campaigns I have done were focused on measuring directly the performance of the thruster using a thrust balance that we have here in the lab, and that you can see in the two pictures above, and to complement those direct measurements with probe measurements. So the main takes from those two campaigns gathered in one are that, first we had to develop a sort of specific procedure to measure the thrust, to isolate the actual displacement on the thrust balance from the real thrust and other external effects, which is not necessarily easy with this type of thruster. We observed, as you can see on the top right plot, the expected behavior that the thrust increases with the mass flow rate and the discharge voltage in the envelope that we could cover. And we saw that the thrust efficiency mostly depends on the anode voltage, that is on the bottom plot. And we reached the maximum for 325 watts, which is a bit more than the expected nominal power for the thruster. And that the thrust efficiency saturates in the range that we covered with the power. As I said, to complement the thrust measurements, we did some probe measurements that give a bit more detail on the sources of losses in this thruster. So the first measurement, the first probe that we used was a Faraday cup that measures the ion current density in the plume. You can see a matrix of various operating conditions, so mass flow rate and voltage. And so for each of these points, we did several angular scans of the plume. And we see quite obviously on those plots that there is some asymmetry in the plume that can be caused by the cathode location, the injector inhomogeneities, the position of the coils, and some alignments of the probe. So we have a rather clear idea of why we have these asymmetries. And from those measurements, we saw mostly that we have a propellant utilization that is large, in some cases larger than 1, which is something typically observed in this kind of thruster, which is possible in the way it's computed in this case, and is characteristic of the possible presence of multiply charged ions. And we also observed that the divergence and the current utilization are quite low, and they're strongly affected by the discharge voltage. Then we also measured ion velocity or energy using a retarding potential analyzer. You can see the most probable velocity on the top plot and the average velocity on the bottom for different operating conditions and different angles. Mostly we saw that from the top plot, the ions that are within the beam come from a single same main ionization region, which is with the sharp drop at wide angle. And from the bottom plot, we can see that on the axis and at wide angles, the slower ions that form the tail of the VDF significantly lower the average and affect the performance. Combining the data from those two probes, we can evaluate indirectly the performance of the thruster, and we saw that there is quite good agreement with the direct measurements, which confirms that despite all the assumptions and the measurement errors, we can still rely on those the information provided by the probes. As a conclusion of this campaign, we saw that the current utilization and the divergence are the main drivers for the losses in this device and are the ones that shape the evolution of the thrust efficiency. And they allow us to identify what must be optimized in the thruster, which is the magnetic topology. And the objective for future iterations would be to increase the anode shielding, to have less electron current towards the anode, and maximize the ion current in the beam and the thrust. Something else that we observed in this campaign is the evolution of the frequency spectrum of the discharge current that you can see in the bottom plot. We saw that it seemed like there was some correlation between the frequency spectrum and specifically the presence of high frequency oscillations with high discharge current mode. So we tried to correlate the evolution of the spectrum with the variation in time of the discharge properties that you can see on the right and the displacement of the thrust balance. This shows the evolution, as I said, of the high current. So on the top plot, you can see the high current mode with a very strong high frequency oscillation that then shifts towards a lower current mode in steady state with lower frequency oscillation. We did some preliminary analysis of the peak coherence, the self-peak coherence of the discharge current, which is the plot, the color plot you can see in the middle. And this showed that there is nonlinear coupling between several of the oscillations that we see in the spectrum. This explains the presence of harmonics of both the low frequency oscillation and the high frequency, as well as interaction between the two, which gives frequencies such as combinations, as written here, of the two frequencies. We have some candidates for identification of those oscillations, but this is still an ongoing work. And we observed as well with this change in frequency and current that it affects the ion energy. Even though the discharge current decreases, the current density, the ion current density in the beam increases, as you can see on the top right. Those are RPA measurements, so ion energy. And the ion energy decreases, but we still observe an increase in performance and a decrease in power. So overall, it looks like these modes have to be better understood and better controlled because they happen spontaneously, they change spontaneously, and that they might very well have something to do with electron transport, which is a big question in Hall thrusters. To conclude, what I have left to do in my PhD is to conclude a journal paper that I am writing right now and to write the thesis. And a potential continuation for the research on Hall thrusters in our lab would be iteration of the design of the thruster I tested that other results are presented today. Further test the new 100-watt thruster that we ignited recently, develop our hollow cathode, and work on test bench and investigation of instability in Hall thrusters. And those are my achievements that I've done throughout the PhD, several conferences, one publication, and hopefully another one that will be submitted soon. If you have any questions, I'll be happy to answer.